Hello and welcome to today's IWCS webinar. My name is Connie and I'll be your Cisco WebEx producer for today's event. Now, I am pleased to turn the webinar over to Ed Fitton, your IWCS moderator. Ed, please go ahead.
The IWCS webinar series event is hosted by the International Cable and Connectivity Symposium. I am Ed Fenton, a cable industry advisor working with the IWCS team. As Connie said, if you have questions, please use the Q&A box on the bottom right of your screen to post a question anonymously. If you wish to contact the presenter or IWCS after the presentation, you will be given the contact points at the end of the webinar. Please note that IWCS does not distribute the presentation slides from either our conference sessions or these webinars. However, please feel free to contact the presenter directly, and they will respond individually to you. Today, we welcome Doug Duke, Senior Applications and Development Engineer for AFL in Duncan, South Carolina, USA, who will be presenting his paper on issues concerning dissimilar single-mode fiber splicing. Doug Duke is a Senior Applications and Development Engineer in Splicer Engineering at AFL. After receiving his Bachelor of Science in Mechanical Engineering from the University of Texas at El Paso, Doug joined the Defense Systems and Electronics Group in Texas Instruments and worked primarily in the development of airborne radar and infrared detection systems. Since joining AFL in 1991, he has worked continuously in engineering activities related to fusion splicing of optical fibers. In his more than 25 years as a splicing engineer at AFL, Doug has guided splicer product development, authored and presented numerous technical papers, conducted seminars on fusion splicing technology and applications, and is named in several patents. Doug, we welcome you to present at today's IWCS webinar series event.
Ed, thank you for your introduction, and Connie, thank you for all your work in setting this up. And before I begin, I also want to thank David Cadu of IWCS for giving me this opportunity, and also I'd like to thank Patricia Hudak, who was very helpful in aiding me in terms of the original submission of the paper and the presentation, and one more person, and that is Bertil Arvidsson, who was the chairman of the session at IWCS 2017 where the original paper was presented. And actually, he, in the question and answer session after the presentation of the paper, I thought he asked one of the best questions. And that question was, why didn't we present this paper before? Why didn't we prepare this paper before? And it was an excellent question on a number of levels, and frankly speaking, I hope that those of you who have been able to participate in this webinar will find the information useful. We thought, based on our work with fusion splicers here at AFL, that this information was important, and there had been a number of questions raised by our customers when they would call in for service and support, in particular about dissimilar single-mode fiber splicing. And these issues have become more and more important over recent years. So if we look a little bit at the history of single-mode fiber splicing, in the history of single-mode fiber splicing, if we go back to when I joined this industry, which was about 26 years ago, most single-mode fiber splicing were simple SMF-28 or similar fibers, G.652 fibers spliced to themselves. And then in the 1990s, we started to see some dispersion shifted fiber, and then the G.655 non-zero dispersion fiber. And so at that point, we started to see some single-mode fiber dissimilar splices. But for most customers, that wasn't an issue. It was really the long-distance companies. But in the last decade, we've seen a proliferation of new fiber types, particularly the G.657 bend-insensitive types, which are very valuable for fiber-to-the-home deployments. And and even more recently G.654 fiber type. So what has happened is dissimilar single-mode fiber splicing has become a lot more common, and it's caused a lot of confusion sometimes in the industry, especially when these fibers are spliced with a really high-quality splicer that has a very good optical system. And so that's what we want to talk about today. We want to address some of these issues in terms of the appearance of the splice, because there can be a shadow or a line at the splice point where the two dissimilar fibers come together. And we want to discuss what the possible implications are, or are there any implications in terms of splice loss and the integrity and strength or long-term reliability of the splice. Okay. So one of the things that has happened is that sometimes there's confusion when a line or shadow occurs at the splice about whether or not it represents contamination or a bubble at the splice. And so some of the things that can so if we go on to the next slide, we're seeing the factors that affect the splice appearance. So if we have an actual contamination or actual bubble, that is obviously a concern. And poor arc conditions, especially a weak arc power, which could lead to really an incomplete fusion, that could be a problem. But dissimilar left and right fibers also affects the appearance of the splice. And again, we'll show a lot more detail of that. Now, if we go to the next slide, let's talk instead of the factors that affect the splice appearance, rather to the factors that affect the splice loss. Obviously, for the discussion today, we're really talking about high-resolution single-fiber splicers that are capable of performing core alignment. So if we have poor core alignment, that's defeating the entire purpose of the fusion splicer. But a bubble or an actual splice defect, an occlusion, or some kind of contamination could certainly affect the loss dramatically. The other thing is if we're splicing dissimilar fibers, there could be a difference in the MFD between the right and left fibers, and that will have some effect on the splice loss, although in the case of dissimilar single-mode fiber splicing, it's typically moderate. If the splicer itself has not been maintained as well as we might hope, then the arc conditions might not be what we want, and we might not be heating the fiber the right amount, and that can affect splicing in quite a number of ways, not all of which we'll discuss today. Moving on to the next slide, let's focus in a little bit more at bubbles on the splice point. So a bubble will typically be recognized as a dark spot in the fiber image, and this can trigger an alarm in the fusion splicer, a bubble error message. But sometimes that error message is triggered by some other dark line, for example, in the splice point. So it may not be an actual bubble. So we're going to want to talk about that a little bit more. Now, there could be contamination on the surface of the fiber that really won't affect the splice loss. So some of the causes of the bubble, the most common cause is probably going to be contamination on the cleaved fiber end. So, after cleaving the fiber, the end of the fiber is pristine, and we want to load that into the splicer and make sure that we haven't touched the end of the fiber against something to contaminate it, because any contamination could outgas during the arc and form an air pocket, a gas pocket, or a bubble. The other thing is, especially in the case of multimode fiber, which really isn't our topic of discussion today, but in the case of multimode fiber, during the beginning of the arc, the heavily doped core of the fiber can actually melt back a little bit due to its lower melting point, and if the two fibers are stuck together at that point, we could trap a little air pocket. So the way we deal with that is we just modify the arc parameters and give the fiber a little bit more time to heat so that it transitions from a concave to a slightly convex shape before the two fibers are joined together. So preventing actual bubbles, we want to avoid cleave contamination, load the fibers carefully, maintain the performance of the cleaver to make sure we're not inducing a problem. And then, of course, in the case of multimode fiber, make sure that we have the proper prefusion time to heat the fiber in sufficiently. So let's move on to some discussion of the bubble alarm and detection that I mentioned previously. So any dark spot in the splice image may trigger a bubble error message. Now, with the more sophisticated splicers that we have today, typically the alarm threshold can be altered if necessary to reduce the sensitivity to an alarm. But any dark spot that is larger than the error limit threshold will trigger the alarm. So it is possible that the error message can be triggered by a line at the splice point, even if there is not an actual bubble. In terms of the appearance of a bubble, it usually appears as a dark spot that is round, not a vertical line at the splice point. And in many cases, the shape of the fiber has been deformed as the bubble expands. So if the bubble error message is triggered by a vertical line or a shadow at the splice point, one of the things we're going to want to do, especially if we know that we're dealing with dissimilar fiber splicing, is just modify that error threshold. So if we move on to the next slide, you can see a comparison of a rather dramatic large bubble and defect in the left-hand image. And on the right-hand image is really the primary subject of discussion today, which is a vertical line at the splice point. And in particular, in this case, you can see that line where the two fibers come together is dark on the right-hand side and lighter on the left-hand side. Now I'll explain why that happens later. But in both cases, it's triggered a bubble alarm. So what we would want to do with the image on the right-hand side is if we recognize that with the information that I'm presenting today, we would modify the alarm limit. So one of the things, moving on to the next slide, let's talk a little bit more about determination of an actual bubble. Obviously, one thing is that the appearance can be very different from the vertical line, but sometimes there can be a spot less dramatic than what we saw on the previous slide, and we may not be sure if it's a bubble or if it's some dust or debris on the outside of the fiber, which may be inconsequential. So one thing we can do is re-arc and see what happens with the dark spot. Typically, if we do have a bubble or a gas pocket, if we heat the fiber enough, perhaps re-arcing several times, that bubble may expand and it may actually blow through the outside of the fiber. On the other hand, if the black spot decreases in size when we re-arc, then probably what we're doing is we're remelting the surface of the glass, and the defect is disappearing because it's not an actual bubble. So if we move on to the next slide, you can get a representation of that. So you can see here the initial appearance after splicing is shown in the leftmost image, and if you look carefully, we're seeing both the perpendicular X and Y camera images of the spliced fiber, and there's a little spot in the upper X-hand image. After we re-arc one time, that spot gets a little smaller in this particular case. We still see the bubble alarm. After we re-arc another time, the bubble alarm is now eliminated. There's still a very small spot, but it's below the alarm limit threshold. And when we re-arc one more time, in this particular case, the spot is no longer visible. So in this case, it was not an actual bubble. It was some small defect or some dust on the outside of the fiber. And so this can be caused in some cases by just having a little bit of a large score mark from the cleaver. So this would be an example of something that's really inconsequential and unimportant. So let's move on to the next slide, and this is, I want to introduce and talk about the optical system of the splicer, because that will lay a better foundation for the rest of this presentation. So moving to the next slide, we see a representation of the optical system of a typical core alignment splicer. So there are two cameras that look at the fiber from two perpendicular views, and these are high-resolution cameras, and they are capable of focusing to a very precise position relative to the fiber in order to detect the position of the core relative to the cladding. And the fibers are backlighted by collimated light from LEDs. So let's move to the next slide, and let's consider a single axis to explain how the optical system works a little better. And Connie, if you'll click, now we can see the backlighted fiber as it goes through the fiber. It's bending. The light is collimated, but when it hits the air glass interface at the outside of the cladding of the fiber, it sort of fans inward. And actually, and the reason that's happening is the index of refraction of air is lower than that of glass. So it's kind of like looking into a pond. When you look into the pond, things under the water are not exactly where you think they are because the light is bending. And the same thing is happening here. And the amount that the light bends is due to the difference in the index of refraction between air and glass and also the incident angle. So that's why the light rays that hit towards the outside of the fiber bend inwards more than the ones that are close to the center. And that's why the light is all kind of fanning inwards towards the center of the fiber. And the same thing happens at the interface of the core and the cladding, and and this is a typical simple G.652 single mode fiber, so the core is going to have a higher index of refraction than the pure silica cladding because it's doped with germanium. So please click the mouse again, Connie. And so we choose a focus position that will enable us to see the position of the core. And if you click one more time, Connie, we get an image, a resulting image that looks like this. So at the very top of the fiber and the very bottom, the image is completely black because all of the light rays from the LED have bent inwards. So the light is focused in at the center, and due to the secondary bending of the light at the core cladding interface, there is a very bright streak down the center of the bright region. And that is what tells us the position of the core relative to the cladding. So this is really how a core alignment splicer operating by the PAS system works. It all has to do with how the light bends due to any difference of index of refraction that the light encounters when the backlighting behind the fiber travels through the fiber. And as I mentioned, the focus position is very important. And if we go to the next slide, you see a little bit better graphical representation of everything that I've mentioned. You can see the collimated light coming in, the light bending inwards at the cladding surface, and then bending inward again at the core. The position of the focal plane is very important in order to get a good bright streak down the center of the bright region so we can properly align the core. Now, if we consider what the splicer is doing, it's using scan lines. In order to image the data. So if we imagine a scan line from the top of the camera image to the bottom, when we go to the next slide, we see a representation of that scan line. So the background brightness from the LED, you can see that has been highlighted towards the right-hand side of this graphical representation. So that's just the brightness output of the LED. And then it's very dark, as indicated, in the outside areas of the fiber image. And then where the light has been concentrated inwards, which is the area that's circled with the red dotted line, that's where we can see a very high peak in the brightness profile, and that allows us to tell the position of the core relative to the outside of the black region, which tells us the cladding diameter. So to understand a little better what's going on today, let's move on to the next slide, and let's differentiate between radial refraction and lateral refraction. So we're using the radial refraction and a very careful focus position to find the position of the core. But when we splice two different fibers together, we have to not only think about the difference of index of refraction due to the core versus cladding and air, but also the difference of the index of refraction or the refractive index profiles of the left and right fiber. So, as you can see in the radial refraction diagram, the light tends to bend inwards towards the area of higher index of refraction. It does that when it goes from air into the cladding, and it also bends inwards at the core cladding interface. So if we have a higher a fiber on one side that has a higher index of refraction than the fiber on the other side, then the light bends in that direction. We can see this perhaps in a little more detail on the next slide. And so in this case, we can see that if you look at the fiber image, there's a line at the splice point. It's a little brighter on the right-hand side and a little bit dark towards the left, which means that the light has bent towards the right-hand fiber. So let's move on to the next slide, and we can see a couple more examples of dissimilar single-mode fibers. And these are just presented just simply as examples. So the image on the left is a bend-insensitive G657 fiber to a standard SMF. And then on the other side, on the other image, we see a depressed clad single mode to a common match clad single mode. So we wanted to provide a little more in-depth information that illustrates this. So moving on to the next slide, we decided to choose some fibers for a case study. And if we go to the following slide, you'll see the fibers we chose. As kind of a control, we included in this study normal single-mode fibers spliced in normal single-mode. And then we chose a normal G652 to a 654, which is a fiber with a pure silica core. And then we did a 652 to a non-zero dispersion 655. So moving on again to the next slide, one of the things we did is we measured the mode field diameter of all the fibers in our study. And we also wanted to look at the refractive index profiles, because that really has to do with why the light is bending the way it is. And we're very grateful to the help of Andrew Yablon at Inner Fiber Analysis for providing the refractive index measurements. So let's move on to the next slide, and we'll show you the mode field diameter measurements of the fibers that we used in the study. And so you can see the measurements of the 652 standard single mode to the pure silica core 654 and the non-zero dispersion shifted fiber. So the 652 and 654 fibers, the mode field diameter difference is relatively small, but the mode field diameter of the 655 fiber is small relative to both of the other fibers. So if we just use the classical equations for calculating loss due to the MFD difference, when we're splicing the 652 to the 652, obviously the difference in mode field diameter really doesn't exist. So we would expect little to no contribution of mode field diameter difference. In this particular case, with this particular G652 to G654 fiber, there's a small but really negligible loss due to mode field diameter difference. But on the other hand, when we splice the standard single mode to the non-zero dispersion G655D fiber, there's a rather significant contribution to splice loss due to the mode field diameter difference. So let's move on now, and we will look at the refractive index profile and the appearance of these different splices. Moving to the next slide, you can see the refractive index profile for a standard single-mode fiber. And in this case, it's just a pure silica cladding and a germania-doped core. And you actually see a dotted line graphical representation and a solid line representation. And I won't discuss this too much, but essentially, when we heat the fiber, the refractive index changes a little bit. And the reason for that is when the fiber is created in the manufacturing process, when it's drawn, there are some residual stresses in the glass. When we heat the fiber, those stresses are relaxed, and so the refractive index changes slightly. Moving on to the next slide, you can see a left to right grayscale representation of the refractive index. And you can't really, the human eye can't detect it, but in the center of the splice point where the yellow dotted line is, the refractive index is a little bit higher than it is to the left and the right. And the reason is that's the area of the fiber that has been heated and relaxed, and therefore the refractive index changed. Let's move on to the next slide, and let's look at the appearance of the splice. And at first, what I'm showing here is a oil immersion microscope image. So this is not an image from the splicer itself, but if you look, you can see a very small line in the center part there is the core. The cladding is almost the full width of the image, but where the core of the two fibers come together, you can see a very slight line. But it's very, very hard to detect because this is just SMF spliced to SMF. And Connie, if you mouse click, here we can see the image from the splicer itself. And again, there's not much we can see. It almost looks like a continuous fiber that has never been spliced, which of course is what we want it to look like, because that means it's a good quality splice. Now let's look at the refractive index profile on the next slide of the G652 standard fiber as compared to the 654. And we've overlaid the refractive index profile of both fibers on the same graph, and we actually had to increase the vertical area that we're showing in the refractive index. And the reason for that is in the G652 fiber, the cladding is pure silica, but on the G654 fiber, the core is pure silica, and the refractive index of the cladding has been doped probably with fluorine to reduce its refractive index relative to the pure silica core. So overall, the refractive index profiles look very similar, but the entire refractive index profile of the G654 fiber is lower than that of the standard G652. So let's go on to the next slide and see if we show a graphical representation, again showing the 652 fiber on the right, the 654 fiber on the left. It's a little hard to see with the human eye, but in this grayscale, darker means higher index of refraction, and so the pure silica cladding of the 652 fiber is about the same refractive index of the core of the 654. Let's move on to the next slide, and here we see once again the oil immersion microscope image. And in this image, you can see that in this microscope image, there is a vertical line at the splice point, and it's dark on the right side and light on the left side. And remember what I said before, the light wants to bend towards the higher index of refraction. So since the G654 fiber has a lower index of refraction across its entire refractive index profile, the light where the two fibers come together is dramatically bending towards the standard single-mode fiber. And Connie, if you mouse click one more time, we see exactly the same effect in the image on the splicer, and it's quite dramatic. It's quite dark on the 654 fiber side, quite light on the 652 fiber side. So let's move to the refractive index profile of our last fiber combination. And it's a little difficult to make out the dotted line refractive index profile of the standard single mode fiber versus the solid line of the 655 non-zero dispersion fiber. But you'll notice a couple things. One is that the peak refractive index of the core of the 655 fiber is much higher than that of the single mode fiber, and also it has a couple of high refractive index areas outside of the core because there's a ring structure surrounding the core. Now, if we move on and show that graphically on the next slide as the map of the refractive index profile, once again we can clearly see the difference in the refractive index profile. We have a larger dark area on the 652 fiber for the core, a narrower, smaller area on the 655 fiber, which is darker, and then a shadow above and below that because of that ring structure. And moving on to the next slide, you can see that we see something very, very similar in the oil immersion microscope image. And again, Connie, if you'll mouse click one more time. Once again, in the splice image, it's much more difficult to see it, but if you look very, very carefully on the 655 fiber, you can see that the brightness pattern in that bright central region is a little more complicated than it is on the 652 fiber. So let's move on now and let's talk about the splice results with these three combinations. This is what we really want to get to. And so here we see the splice loss results. And you remember before I said that when it comes to the 652 to 654 fiber, the mode field diameter of the two fibers is very similar. So actually it's very difficult to distinguish between the very low splice loss results with the standard single mode splice to itself versus the standard single mode splice to the G654 fiber. But remember, this was the most dramatic appearance of the bright line of the three fiber combinations. Now on the 652 fiber spliced to the non-zero dispersion 655 D fiber, we see that the splice loss results are nowhere near as good as the other two fiber combinations, and that's due to that large mode field diameter difference. So let's now go to the slide that shows the splice strength results, and this is the typical Weibull plot distribution where we use a log-log scale to show in the vertical axis the cumulative failure probability versus the strength on the horizontal axis. And actually the strength results for all three of these fibers, those distributions look very similar. And so what we're seeing that even though the refractive index profiles of these fibers are quite different, in terms of splice strength, it's meaningless. And so really what we're seeing from this is the appearance of this dark line, although it might intuitively be troublesome to the splice operator, it really doesn't indicate any problem with splice strength. So let's summarize the splice loss results on the following slide. And so we see a dramatic vertical line with the 652 to 655 fiber, but it has no effect on strength, and it really doesn't mean anything in terms of splice loss. Whereas with the right-hand image, where we're seeing the 652 fiber to the 655, even though that image looks almost as uniform left to right as the left-hand image of the standard single-mode splice to itself, frankly speaking, that fiber combination represents a higher average loss due to that mode field diameter difference. So let's move on to our conclusions. So I think the first thing to understand is that a large refractive index difference between two fibers can easily result in a quite visible line, which to the untrained eye can be disturbing. But this line is due to the way the light is bending, and to a lateral bending of the light due to the differences between the two fibers. And the larger the difference between the refractive index between the two fibers, the larger that vertical line is likely to be. So this is in effect due to the backlighting of the fiber, so that we can image it with our splicer camera, but it is not related to the transmission of light, optical power, or communication signals down the length of the fiber. So it's really not directly related to splice loss. And moving on to our final conclusions, a visible line in the splice point is not really a reliable indicator of any problem concerning splice loss or strength. And I think the three fibers that the three fiber combinations we chose were chosen to really illustrate that. So on the 652 fiber splice to the 654 is a very prominent line. It's very visible, but the loss is very low. Whereas with the 652 splice to the 655, there's almost no visible line, but the splice loss is relatively high due to the MFD difference between those two fibers. So really we can't relate it to splice loss, and also there's no relation to splice strength. On the other hand, if we know the mode field diameter difference between two fibers, that is a very good predictor of splice loss, as we've seen in this case, because that is actually related to the transmission or the coupling loss at the splice point. So with that, that concludes this presentation, and I want to thank everybody for participating.
And thank you, Doug. At this time, we will ask as many questions from the attendees as time permits. And we'll start with this first question. Are splice points in fibers often susceptible to failures or increased attenuation?
Well, I think if we're talking about fusion splicing, there are many things that come into that. I would say, first of all, in terms of increased attenuation, unless something rather dramatic happens, a fusion splice really has typically very good integrity and doesn't really change due to atmospheric or temperature conditions unless there is somehow some dramatic stress on it that causes it to break or something like that. So, you know, if you do a good fusion splice and it is properly welded together and you put a good heat shrink sleeve on it to protect it, the integrity is very good. Now, if we were going to talk about mechanical splicing, it's a completely different subject, because there we haven't really welded the glass together, and temperature effects or humidity or things can cause some variation of attenuation or in some cases even a dramatic failure.
Thank you. Next, do bubbles at the splice point occur as a result of splicing dissimilar single mode fibers?
Typically no, but unfortunately, due to the alarm threshold in the software of the splicer, it may result in a bubble alarm, which I illustrated earlier in the presentation. So that's why we wanted to present this paper, to kind of differentiate between those two things. But typically the difference between the two fibers itself is not a cause of a bubble.
Okay, thank you. Next, of the three fibers tested in the case study, which results best represent a G.657? And then the second part of the question was, why was G.657 by not tested?
That's a very good question, and actually, that's almost the same question that the chairman at IWCS 2017, Bertil Arvidson, asked me. Frankly speaking, in retrospect, we wish we had included a 657 to 652 combination, because really that's more important in the marketplace today. It's very, very common. Instead, we chose the 654 to 652 combination because it represents almost a worst case scenario in terms of the two refractive index profiles. So I'd say the answer to your question is that in terms of what we see at the splice point and the splice loss results, the most similar combination that we used was the 652 to 654 fiber combination. A lot of the 657 to 652 combinations show a similar vertical line, but it's not as dramatic as the 652 to 654 combination. Also, typically, the G657 fibers have a little bit smaller mode field diameter than the standard 652 fiber, but usually the fibers have been engineered so that mode field diameter difference is relatively small and has a relatively small effect on splice loss, because that is a really desirable characteristic for a 657 fiber.
Thank you. Next, how is the splice loss between G652D and G657 B2 and B3 fibers?
Typically, it's going to be a little bit higher than a 652 to 652 splice. So whereas with a typical 652 to 652D to 652D fiber splice, with a really good core alignment fusion splicer, our average splice loss might be in the 0.01 dB range, with occasional splice losses of 0.02, 0.03. We're going to be a little higher anytime we're splicing a 657 of almost any type to a 652D. So we might have an average loss of more like 0.03, or in some cases 0.04. It just depends on the characteristics and principally the mode field diameter of the particular 657 fiber that we're splicing to the 652D.
Okay, thank you. Next, you mentioned weak arc power is possible for a bubble.
Rarely. It's more likely to cause maybe a little bit of a shadow, but frankly speaking, weak arc power usually, in most cases, doesn't have a dramatic effect on the appearance of the splice. It's more likely to affect the strength. So we have seen instances where the appearance of the splice was almost normal, but if the arc power was a little weak, then during the proof test that the splicer typically administers to measure the strength, the splice will break. So if somebody experiences that problem, I would recommend that they immediately perform an arc calibration and make sure that the heat output of the electrodes is correct.
Okay, thank you very much. At this point, I would like to point out that there are a number of other questions. We are unfortunately out of time. There is an opportunity for questions to be asked outside this presentation, but at this point, we do need to conclude. So I wanted to thank you, Doug, for presenting this very interesting and important topic today. Please note the contact points being shown should you wish to contact Doug after today's event. Each of these IWCS webinar series presentations events are recorded and will be archived on the IWCS.org website. It normally takes up to 2 weeks for these to be posted. The IWCS webinar series will conduct presentation events on a monthly basis. Webinar events will take place on the third Friday of each month at 10:30 a.m. Eastern USA time. Our next scheduled event will be on Friday, May 18th at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for the event a few weeks prior. Please feel free to share our announcements with your colleagues so that they can join in and register as well. For over 66 years, the IWCS International Cable and Connectivity Symposium has been the recognized leader showcasing new technologies in cable and connectivity products, processes, and applications. Our next annual international conference will take place on Sunday, October 14th through Wednesday, October 17th, 2018, at the Rhode Island Convention Center in Providence, Rhode Island, USA. In addition, the third annual UL and IWCS China 2019 Cable and Connectivity Symposium will take place on Tuesday, March 26th through Thursday, March 28th, 2019 at the Shanghai International Convention Center in Pudong, China. Please visit our website at iwcs.org for more event details. In just a moment, you will see a brief survey so that you can provide us your feedback and comments on today's event so that we can further improve this webinar series for you. Thank you for participating, and this concludes today's event.